Alrighty, so next up we've got Ellie from APNIC and I think Sophia as well. Very good.
Okay, good afternoon everyone. Hope you're wide awake after your lunch break. So we're going to do something slightly different for the APNIC update this time. So we're going to break it up into two parts. So I'm going to talk about a project which is APNIC Services Initiative that we've been working on, and my colleague Sophia, hopefully you've already had a chance to meet her, she'll be talking on the product side. So I'm going to attempt to work this clicker. Okay, great. So who is Accuracy and how can you help? Well, there are many of you in the room who have applied directly to APNIC for IP addresses and AS numbers in order to provide services to your customers, or you have an infrastructure that has a genuine need for portable address space. Now, when we delegate these resources, we register them publicly within the APNIC Whois database. And this represents who is actually the custodian of that IP address space and AS numbers, and who is responsible for maintaining them. So there's been a lot of discussion within the community from various stakeholders about how we keep the contact details registered within these resources up to date. So this is an issue not only being faced by APNIC, but it's also being faced by other RIRs as well. But this is an initiative of what APNIC has been working on in order to tackle the contact issue, which are referenced within resources. So we've called this project Whois Accuracy Support. And what this project is really to engage our members to review and update their contact details every 6 months. So it's actually been recently implemented within my APNIC. It's there, it's visible. But we're going to be sending more communication about this soon. So we totally understand that there are many of you in the room who have your own internal systems which you use in order to manage your resources. Now, some of you have openly admitted that you only go into my APNIC in order to apply for more resources or to initiate transfers. So we've taken all the feedback on board and we've really looked into a way which we can really make the process easier in order for you to update your contact details, so making it much easier for you to do this, and also making it the process easier in order for our corporate and technical contacts who are responsible for maintaining the resources, how to navigate the process within my APNIC in order to keep their contact details up to date. So one of the ways we've looked at doing this is creating a process where you can update this within my APNIC, these contact details, at a single point. Oh, okay. Sorry. Okay, so the actions that will be required for our corporate and technical contacts during their process, it will be divided into 3 steps. So for these corporate and technical contacts, they will be required to update their membership contacts, their organisation details, and their incident response contacts. And what will happen is every 6 months, each of the corporate and technical contacts registered under an APNIC account will receive an email asking them to do this. So this is just to provide you an example of what this email will look like. During this 6-month period, you'll get this kind of email. Now, all you need to do is, if you have My APNIC Access, click on the link embedded within the email, enter your user and login details, and it will take you directly to this page, which will look like this. So here you can see what the point of contact review looks like. You can see it's been divided into 3 steps. Very nice and easy. So if we go into step 1, into step 1, this is what it looks like when you go to the page in order to verify the contacts who are responsible for maintaining your resources held under your account. So it's a very easy process. You can either edit, delete. In this example, we're choosing to delete a contact, so you just click on the delete button, delete the contact, and move on to the next step. So once you've completed a step, you'll notice you'll see a little tick button beside it, and you can move on to the next one. So if you move on to step 2, this is the area where it contains all of the business details relating to your organisation, which is registered within the organisation object within the APNIC Whois database. So once you've updated it, then you can move on to step 3, which lists the contact details registered within your IRT objects within the APNIC Whois database. Now, I want to point out, the larger the organisation you are, the more likely you are to have a few different IRT objects registered under this step. Now, as a particular contact, only particular contacts may have maintainer password details to update a particular IRT. So depending on whether you have those maintainer details registered under your My APNIC login is a variant which is a factor of whether you can update the IRT object or not. So if you choose, what happened here? Okay, so if you choose to update an IRT object, this is an example of what the screen would look like. And once you've completed all 3 steps, then you'll get a completion message along with the timestamp. Now, it's important to point out a few different contacts under your account can go through this step, depending on whether you're a corporate contact or a technical contact, depends on what steps you have access to update or not. So for example, corporate contacts can update steps 1 and 2 because they have that level of access. Technical contacts can update steps 1, but they will require verification from the corporate contact in order for those changes to be implemented. A technical contact can also view the organisation details, but they are not able to change them. So it really depends on what contact type you are as to what you can update and change. So there's going to be more information provided about this shortly via blog post and FAQ. There are going to be future changes, so this process is going to be built on. So in future, there's going to be a step 4 where person objects and role objects are also going to be included in this process. Something that I have to make you guys aware of in this room is we're going to implement Prop 125. So this is covering the validation of abuse mailbox and other IRT emails sometime in the 2nd quarter. Now, why you need to be aware of this? This is where Every 6 months, contact emails which are registered within, listed within an IRT object, such as the abuse mailbox, the email, admin C, text C, they will all require, there are contact emails which will all require verification every 6 months. Now, the person who is responsible for maintaining the contacts under that IRT object will require manual intervention, so there can be no automation in that at all. If there's no response and all those contact email addresses are found to be updated, then what will happen is it's going to be escalated to the LIR concerned. If we're still not able to get in contact, then they will actually be, those contact email addresses will be listed as invalid within the APNIC WHOIS database. And then if further, after every response where we've tried to get in contact, it will be seen as a breach in policy. So this policy actually does have impact, especially on some of our larger members who receive a large amount of email responses to their IRT contact email addresses every day. So it's something for you to be aware of. Sometimes there's, and we're looking about how we implement this policy to make it as easy as possible for our members. So last thing I just want to point out is Apricot will be taking place in Korea in the last 2 weeks of February. There's a lot of policy discussion, policy proposals that are up for discussion. The main one which may have impact for people in this room that I just want to point out is there's one policy proposal. If there are any of you in this room who are currently on the waiting list, who have been on the waiting list for a while and you're near the top of it, then there's one policy proposal which talks about abolishing the waiting list. So if you're one of those people, you are passionate about that, you have a bit to say, I encourage you to have your say because you guys are the ones who decide whether consensus is reached or not. If you don't have your say and consensus is reached, then you just need to lump it and wear it. Okay, thank you. I'll hand over to Sophia.
Hello. Hello to those looking at your screens as well. Hello, welcome back. I hope you have enjoyed lunch and you're awake. I've been talking to some of you, so some of you already have met me, but this is my first NZNOG meeting, so I know lots of you don't know me. I'm Sophia. I joined APNIC about 2 years ago as a data scientist, but about a year ago I changed roles to a product management role, and apart from making it harder for my parents to understand what I do, it completely changed the things I do at APNIC because I was on technical roles. Before APNIC, I was with LACNIC for 4 years, or most of the time on technical roles, and I'm a product manager dealing with people instead of computers and routers. And it seems people are even more complicated than routers. So I'm learning and trying. I've been having conversations with some of you, and I'm trying to understand real needs real people have, because that's what product managers do. Apparently, we have to understand problems, make sure there is a problem first, and find a solution for that, instead of coming up with great ideas, build a solution without even validating that. So product management is something relatively new at APNIC. We started about 2 years ago with first an experiment, and we decided to implement this framework. And a question I get quite often is, why does APNIC have products? So that's why I wanted to start explaining a bit more about that. So it's not that different from what we've always done. And this clicker is tricky. There it is. So we've always been trying to be close to our community. As Ellie was mentioning, we encourage participation. We always have like surveys, we receive calls and emails, and we participate in different events like this meeting. But we wanted to take the ability to respond to that to the next level and get even better at like taking action based on all that feedback that we receive. So we now have 3 product managers. I'm just one of the 3. You may already know Adam, who used to be a policy officer. He's a product manager now, and my colleague George Michelson has recently taken a role as a product manager as well. And we have, each of us have like a set of products we manage. In my case, I have a product family we call information services. So I wanted to present a bit of an update on what I'm working on, and some of you may now understand, oh, that's why she was asking all those questions. So my first product is a network security product. We went through a very nice internal process of finding a name for it, and we recently called it Dashboard for Autonomous System Health. We're currently working on an MVP. The plan is to be ready with that MVP before our conference next month, so we can do some testing during the conference. So the hypothesis is that some of you, and those are Yoshi and Julian, let me introduce you to them. So as part of implementing this new product framework, we came up with what we call APNIC personas. So it's the way we make sure we are developing products for like real people in the community who have real needs, and the way we represent those needs and we make sure we understand each other when we talk about products is using these personas. So when I talk about my product, I say, okay, for example, my network security product, it's for Yoshi and for Julian. So Yoshi is a senior network engineer who has a need for information about his network and wants to detect security issues. But also Julian, who is probably more strategic, wants to have a high-level view and be able to compare how his network is doing with other networks. So with that hypothesis in mind, we went do some validation. In our last conference in New Caledonia, we had some testing a solution with mockups. And we got great feedback, so we moved on to starting with this development of an MVP. So that's a screenshot of how it will look like. So organizations holding an APNIC login can log into this product and see daily hits we are getting from our honeypots. So we have this is a project we already had. It was a research project, so now we are using data from that project. We have partners who have their own honeypots. APNIC has his own sensors as well. We are collecting all that information about malicious traffic being sent from different networks, aggregating, summarizing that, and filtering for the different APNIC members. So we can inform members, we are seeing malicious traffic coming from your network. This is how much, this is the IP addresses sending malicious traffic, you may want to do something about it. So as I was saying, our plan is next month in South Korea, we will be running some testing. I also have another product on a very, very early stage. This is just at the idea stage, so I'm exploring ideas. Because I was doing research as part of my master's using a lot of BGP data before becoming a product manager, and so I'm a bit biased, and I thought, okay, let's do great things with BGP data. So I started exploring these ideas with the goal in mind of using BGP data. So I was like, yeah, BGP data is great. So I had some interviews in New Caledonia, and it was a great eye-opener because I was asking people about my hypothesis and things that I thought could be great for them. And they were, no, BGP data, yeah, it could be interesting out of curiosity, but as a network operator, it won't really help me in my day-to-day job. And by chance, we discovered that there was a pattern. All the people we interviewed mentioned communication issues. When there are routing issues, prefix reachability issues, apparently the main difficulty is around communications, around identifying who to talk to. especially when there's no commercial relationship. So when the problem is with an AS that is not your direct upstream provider, it was hard to identify who to contact. And even when you knew who to contact, it takes a long time because as they don't have a commercial obligation, they take weeks sometimes to fix, I don't know, some prefix being filtered. So we pivoted on the problem we were trying to solve, and we're now trying to explore those communications difficulties and trying to see if there's anything APNIC could do to help in that space. I also have some other ideas I didn't include here because they are some new ideas, but I will use the opportunity because I will be talking to network operators in South Korea again to also explore those ideas. But if you have in your day-to-day job any frustration, any task you feel, oh, this is so time-consuming, and you think there's anything we could do to help, I'm happy to receive feedback and explore more ideas. Another product, and is something I inherited, so this was developed not under this product development framework, and now I'm trying to bring it in that framework. So it's a bit challenging because there were no problem hypotheses that was validated or not like product design. It was just, we have delegated data, we think the community would appreciate having some nice visualization of that delegated data, and we had the hypothesis maybe, and this again was in retrospective, after having the product thinking, okay, what's the problem we were trying to solve with this? We thought Danny, who is a network manager, could use this information offered through the internet directory to make better network decisions. But again, we went to do some validation. I was talking to a lot of people, and we discovered that no, technical people wouldn't use information about how resources are distributed in the region, comparing one economy to the other, but rather this could be used by internet researchers. So that's how we also pivoted a bit on this, and I'm now trying to understand if there are internet researchers or enthusiasts out there who are interested in this kind of data. If any of you have used the internet directory, it's under stats.apnic.net. I have written two blog posts for the APNIC blog when we launched a new version in September last year, and then a new release with some new features in November. If you agree with my assumptions, or if you don't, what was that? Just went black. Or if you don't, please send me an email or talk to me before I leave today, because again, happy to receive feedback. There are some other products. As I mentioned, there are two other product managers, and I'm not going through all the products, but there are two main ones. So Adam is working on a new My APNIC portal. If you are a member of APNIC, you have probably used My APNIC before for different things. Adam is working on a new homepage for My APNIC to customize it for the users, to offer all the different ways that you interact with APNIC as like widgets. And we have a survey. Please, I guess these slides will be available, so if you can follow the URL and participate in that survey, feedback will be greatly appreciated. And we are also looking for beta test volunteers. If you often use My APNIC, and if you're happy to help us with this, get in touch with Adam, who is like trying to gather people from the community to help with testing this new portal. Another product, and this is George's, is AnySigner. This is the idea of using RPKI for signing anything. So not just to produce ROAS, but having other signed objects. And there are some use cases like letter of authority or delegation of agency for IP brokers, for example, or for signing IRR objects. So as I was saying, this is George's product. If you have any feedback, if you feel that there are other use cases you can think of, or if you feel those use cases are useful, any feedback is welcome. But again, I get the question of how come APNIC is doing product development now? How come APNIC has products? Isn't APNIC a non-profit organization? And yes, we are. The thing is that product management, it was developed mostly for like startups in Silicon Valley, but it's not just for commercial organizations. And product management is not about return of investment. Or maybe it is, but not in the traditional sense of return of investment, where the return is money. For us, because we are a non-profit membership-based organization, the return of our investment is satisfaction of our members, satisfaction of our broader community, even if you are not members. So this is just about understanding user needs better, and as I was saying, making sure we validate everything so that whatever we create is really useful for you. So for the community, this means that we are just asking for more feedback, even more than before, and having lots of user research activities like interviews, user testing sessions, or even just spontaneous conversations like the ones I've been having with some of you during breaks. And as I was saying, validating, trying to validate all the ideas we can come up with. So when I was preparing these slides, I was like, it's a bit selfish to just come and tell you about what I'm doing and asking you to give me feedback. So I was thinking, what can I offer? So what I offer is free technical counseling. So if you have any frustrations, if there's something that is really bothering you all the time about your job, I'm open to listening to your problems. This is a unique opportunity, I know. So I'm sorry I didn't have the chance to present earlier yesterday, so I had 2 full days for listening to problems, but at least we have the rest of the day, and you can reach out to me by email as well. If you come to APNIC conferences, I will be at APNIC conferences as well, so happy to hear about your problems. So in summary, we are implementing a product management framework despite being a non-profit, and again, the return for us is your satisfaction, making sure we create things that are useful for you. And that's why we really appreciate feedback, and we are validating everything we do. And I'm happy to talk about this if you're curious, if you're interested. And whoa, it's your turn now of comments, suggestions, feedback, any questions. Participate, as Ellie was saying. Any questions, comments? Didn't bring any chocolates, but maybe next time I should.
I'll leave it there.
Okay.
Thank you very much.
Thanks.
So next we've got Daniel Efrati, who's come from the UK to talk about gigabit wireless to the home.
Hi everyone, my name is Daniel Efrati, and yes, I did come from the UK. It's a long journey, but I was rewarded by this wonderful summer. Thank you for having me, and thank you to our partner Go Wi-Fi, who first alerted us to this conference. So I work for Siklu Communications. It's a company based in Israel specializing in millimeter waves, and what I'd like to talk to you about today and try and convince you that millimeter wave is perhaps the technology we've been waiting for quite a long time to provide gigabit to the home. So I think that's always been the holy grail. You know, we'd all like to have broadband connectivity unlimited in any way, but of course fiber, which is the best medium, is often not prevalent and is expensive to run to every home. And just to say, I put the word 5G on my presentation, A, because it's quite exciting, but B, just that people know, you know, people think of 5G as primarily a mobile technology, but not only mobile, also true for fixed wireless. You know, the idea is to bring these kind of capacities also in fixed settings, fixed meaning stationary. Okay, so I'm going to talk primarily about 2 subjects today. First, I'd like to introduce you all to millimeter waves, and which is a technology perhaps many of you have not heard about before. And secondly, then describe how we can use this technology, or how you can use this technology to then connect, you know, if you're an ISP or you need to provide any other kind of connectivity, how to bring that about to your customers. So just before I start this, and do I need to point this at anything in particular?
So just press the buttons nice and firmly, the left and the right, and
Okay.
Just hold it up a little bit.
Yeah, there we go. Thank you.
Out there.
Right, okay, great. So just to give you a little bit of a background about fixed wireless access. So fixed wireless access has been tried before, not very successfully, I have to say. So I put down here on the slide perhaps two quite well-known examples. The first maybe to the older generation. So this was an attempt during the telecom bubble, if you like, in the turn of the century to use technologies, fixed wireless technologies, such as LMDS and others, to bring gigabit capacities to the home. That never went very well. And then there was a second attempt a few years later under the umbrella of WiMAX, and that didn't work very well either. And I think now in hindsight we can identify the challenges that were present then and perhaps were missing in these technologies. So, you know, if people are to be interested in wireless technologies, then they need to be at least as good as wireline. You know, otherwise, what's the point? If they're not as good, just use wireline, which everybody's familiar with and everybody's happy with. Secondly, and perhaps not less important, is the cost. So if you are going to use wireless to provide service to people, then it's got to be at a lower cost than wireline. Otherwise, you know, what's the point? Again, use wireline. And I think perhaps the third bullet, which is important in the context of this talk, is a spectrum. So the wireless spectrum, as you probably all know, is a finite resource, and there's only so much of it. And if you want people to utilize it, then you need to have plenty of it so that people do get access to the spectrum. So this brings me back to millimeter waves, and I'd like to try and convince you that millimeter waves does deliver on these challenges and is therefore perhaps the technology that's actually going to deliver, and as I'll show you as well, is already delivering on these challenges. Oh. Okay, there we go. Right, so this is the fixed wireless spectrum. Again, fixed in this context means stationary as opposed to mobile. And there's quite a lot of bars on here. Each one of these bars represents what we call a band in the wireless jargon. So down there on the left, I grouped a bunch of frequencies under the title sub-6, meaning frequencies lower than 6 gigahertz. They're very popular, and I imagine if any of you here have tried doing anything in wireless, you've probably been working in that frequency range in the sub-6. So Wi-Fi 2.4 or 802.11 AC, which is 5 gigahertz, all operate down there, and a bunch of other stuff as well. Then there's the middle region, which I termed microwave. So microwave, I imagine, is quite popular in a country like New Zealand that's quite large, where you want to take the transmission over long distances. So where that's the case, then probably it's these bands which extend from 6 to about 40 gigahertz that are very useful because they have certain characteristics which help them propagate over longer distances. So this was all the case up until about a few years ago, and then the millimeter wave technology, which you see on the right hand of the picture, came along, and that is in 3 primary bands. One is called the V band, which is around 60 gigahertz, and one is called E band, which is divided into 70 gigahertz and 80 gigahertz. Okay, so this is the part of the spectrum that I'll be talking about for a little while now. Oh, I keep going backwards for some reason. No. There we go. Yeah, okay, sure. Right, okay, thank you. Okay, so what is the regulatory situation in New Zealand for millimeter waves? So 60 gigahertz is an unlicensed band, which is great. basically means if you wanted to put up a wireless connection in 60 gigahertz or V-band, you could just do that without speaking to your regulator at all. There's quite a lot of spectrum there, currently ranging from 57 to 64. It's a little bit wider in other countries, so we're hoping to see a change come about here as well. For example, in Australia, they extended the V-band from 57 to 66 a few months ago, perhaps 6 months ago, and they're currently consulting on extending it all the way to 71, which is a situation in the UK, in the United States as well. So if you can imagine 57 gigahertz to 71 gigahertz, that's a massive amount of spectrum. So that's V-band, 60 gigahertz, and then the other band, which, as I said, is called E-band, is divided between 70 and 80 gigahertz. So there's 5 gigahertz in 70 and 5 gigahertz in 80. And that's a license band, which means if you want to put up a link in these frequencies, then you need to talk to the regulator. And I believe the cost is $150 here in New Zealand. So that's all good news, because it means the bands are regulated, the millimeter wave is regulated and is permitted here in New Zealand. So it's just a question of, people who are interested is to just start utilizing it. It just occurs to me, I haven't really discussed the term millimeter wave. So for those of you who know anything about electromagnetic radiation and waves and all that kind of thing, know that there's a thing called wavelength, which is inversely proportional to the frequency. And in these high frequencies, if that's of interest to anyone, then the wavelengths are a few millimeters long, which is why we call these waves millimeter waves. Okay, so what are the main characteristics of millimeter waves, and how are they different from all the other frequencies which perhaps people are more familiar with? So the first thing, I think it's quite obvious from this little diagram that I put on before, is the sheer amount of spectrum available in these bands. So you can see while there are loads of other bands in lower frequencies, they're all quite narrow, meaning the amount of spectrum available there is quite small. Whereas in millimeter waves, you can see by the width of these bars, there's quite a lot of spectrum. This is significant. First of all, it means that the spectrum is uncongested. Okay, there's so much of it, and it means that it's just there for people to use, unlike perhaps some of the lower frequency bands that I've drawn on there, where you can see that the bars are quite narrow. And secondly, it allows us to use very wide channels. So if you've used 5 gigahertz before, or these lower frequencies, you know that the channels come in multiples of 10 megahertz, so maybe 10, 20, maybe 40 megahertz. And if you've used microwave, they come in multiples of 28 megahertz, maybe 28, 56. Here in millimeter waves, because there is so much spectrum, there's a possibility of using really, really wide channels, and by that I mean, channels as wide as 2 gigahertz. And when there are such wide channels to take advantage, then it's possible to pump a lot of bits through these wide channels, and we're talking about air capacities of up to about 10 gigabits per second. Okay, so that means that you can put up a wireless connection, say between 2 points, and that would provide you a connection of 10 gigabits per second. So that's something quite unique to this band. It's not possible to do in any other frequency band. Okay. A second characteristic, which is key to millimeter waves, is the fact that the transmission is very directional. Okay, and this is quite an important thing, because those of you who have had or have experience in wireless, we're always in that field, we're always worried about interference, because we put a link up and it connects point A to point B, and then all of a sudden, and it works quite reliably, but then all of a sudden it doesn't. Maybe because somebody else put another link up, or just the spectrum is overutilized. So in these frequencies, in millimeter waves, the beams that are being transmitted are very narrow. We call them pencil beams in the industry. And you can see, as I put up here, they're typically between 0.5 degree to 2.5 degrees wide, which means you can have a link going in a particular direction without polluting, as it were, any other direction. So this is great for frequency reuse, meaning you can reuse the frequencies again and again. So for example, if I had a wireless connection pointing this way, I could then use the same frequency to implement a wireless link in a slightly different direction. In fact, we say that if there is at least 3 degrees in angular separation, then you can reuse the same frequency, and that's quite significant and quite unique. And of course, the consequence of this is in these bands, in these frequencies, there's no interference, which means if you put up these links, you use this technology, you can rest assured that your link is not going to suffer any interference. And this I would say, is also perhaps proven by the regulatory framework approach taken to these frequencies. Like I said, 60 gigahertz is completely license exempt, but also in E-band, in most countries, it's not true for New Zealand, but in most countries, the licensing mechanism is what we call light licensing, which means people have to do very little to register their links. And this is because the regulator knows that the probability of getting any interference in these frequencies is very, very small, if not, zero. Another consequence of these narrow beams is that the transmission is very secure, because it means that if you're transmitting from point A to point B and anybody wanted to intercept that transmission, they would need to literally be hanging in the line of transmission. They couldn't just put an antenna up maybe a few blocks down the road in the hope of catching any of that transmission. They would actually need to be right within that 1 or 2 degree beam width. And then maybe the flip side of these narrow beams is the fact that because they're so narrow, it's important that any installation of these antennas is done in a very stable way. Okay, so if you're putting these up on a pole and the pole is blowing in the wind and swaying in the wind, and the sway is more than 1 or 2 degrees, and obviously the beam is going to go in and out of alignment, and the performance is not going to be very good. So indeed, those of you who have used perhaps microwave before and are used to quite large dishes, I can tell you that in millimeter waves, the largest antenna that is used is a 2 feet antenna, a 60 centimeter antenna. That antenna will have a huge gain and will have a beam width of only ½ degree, and it's just not practical to use any larger antennas because the beams are going to get so narrow that it's just going to be impossible to align them. So I put a few photos on there just to give you a sense of what these pencil beams look like in reality. So you can see here on the right, for example, this is showing you how these radios can be squeezed together quite tightly without causing interference. And then on the left, that's just a hub and spokes kind of example from Liverpool in the UK, showing a bunch of links emanating from the same point, all operating on the same frequency. And again, that's possible because the beams are so narrow. Okay, so we've got abundant spectrum, that's good. We've got narrow beam width, that's very good. So what are the less favorable aspects of millimeter waves? So the first is that it requires a clear line of sight, meaning there must not be any obstruction in the line of sight. So whereas in lower frequencies, sometimes you can get around partial obstruction, or you can go around corners, that kind of thing. In these high frequencies, it's just not possible. So you have to have a line of sight. I put something else a little bit more technical on here called the Fresnel zone. So those of you who have done wireless before, when you operate in low frequencies, then you know that by clear line of sight, I mean more than the optical line of sight. There's sort of the shape that these waves propagate. It's a little bit like a rugby ball, and it's called the Fresnel zone, and it has to have clearance. And the good thing about millimeter waves, the Fresnel zone is so small, so basically I would say to you, if you've got an optical line of sight, you've got Fresnel zone clearance, so that's good. But if you were going to put up a link between 2 points, A and B, then make sure you can see point B from point A. Okay, and the last thing I want to say about millimeter waves is that this is inherently a short-range technology. Okay, and I'll talk in more detail about that. So V-band 60 gigahertz is attenuated by the oxygen in the air, so it happens to coincide with an oxygen absorption band, and I'll show you that in more detail in a minute. Basically meaning that when these waves propagate through the air, they get attenuated quite heavily, so they can't reach very far. And then both V-band and E-band, so 60, 70, 80 gigahertz, are then attenuated by rain. Okay, so basically when it rains, the performance can degrade, and the more intense the rain, the more severe is the degradation. And also talk a little bit about that and how to go about taking all that into account to provide very reliable connectivity. So as regards distance, I put some effective maximum distances on here. This is very contentious because it is possible to go higher, or some people might be a bit more conservative and they might prefer to go lower, but this is for Auckland, which I understand is sort of the wetter regions in New Zealand. So if we're talking about the V-band, the license-exempt band, that will reach about 1 kilometer. Okay, this is primarily due to the oxygen absorption. And then if we talk about E-band, then I guess it greatly depends on what air capacity you're after and what sort of link availability you're after. So for example, if you're an ISP and you're putting one of these links into your core network, for example, you may have a 10 gigabit ring that you may want to complete using one of these wireless links. So then you'd want the link to be incredibly reliable, maybe, I don't know, maybe 99.995%, and you may need the whole 10 gigabit available all the time. In that case, probably not a very good idea to stretch it over 3 kilometers. But, you know, if you're not that strict and you're happy to live with, occasionally happy to live with a lower air capacity, and that's usually not a problem for sort of Ethernet-based networks because utilization is quite low naturally. Or if you use something called overbuild, where you use 2 types of frequencies to complement each other, and I'll describe that in more detail, then you can stretch it more, maybe up to 10 kilometers or so. Okay, so I talked about the atmospheric absorption, so there's a little graph here showing the absorption of oxygen and water in the air. And as you can see, between the red dotted lines, this is 60 gigahertz, and this is where we have a massive peak, and so we're talking about 15 dB per kilometer. So that's about a 70-fold, meaning after 1 kilometer, only 1 part in 70 remains of the original signals. That's quite significant. This is also one of the reasons this band is license exempt, because the regulators know it doesn't propagate very far. And one thing to say is that the peak, the actual peak is around 61 gigahertz. So the further you get away from 61, the lower the impact of this oxygen absorption, which is why it's nice to have this band extended a little bit. And I mentioned before that in other countries it's extended beyond the 64 gigahertz end, and I'm hoping that New Zealand will follow soon. Okay, atmospheric absorption doesn't really play part in E-band in 70, 80 gigahertz. You can see here it's in between the green lines, so it's quite insignificant, about half a dB per kilometer, so really negligible. Okay, so this is all static and well known. And then I want to just mention the other important factor in link design, which is rain. Okay, so as I mentioned before, rain plays a significant role. It's basically the amount of water in the transmission path. The more there is, the more the signal is attenuated. So before I go into that in a little bit more details, I want to give you the good news, and the good news is that there is a whole bunch of other adverse propagation phenomena that are there in wireless transmission that do not impact millimeter waves. So if you are used to using wireless or planning links in lower frequencies, then I'm sure you'll be relieved to know that all these factors that I've listed here on the right are of completely no consequence at all to millimeter waves. So the first one is interference. That's, like I said, there's no interference in millimeter waves because of the narrow beams. And interference is a really bad one because it's very hard to predict. So you might put up a link and everything might be working fine, and then a few weeks later, a few months later, somebody comes along and puts in another link, perhaps even a few streets away, and all of a sudden your link is no longer reliable. Okay, so there's no, I would say, scientific way of quantifying this. Okay, but of course it's got to be taken into account because when you've got interference, your link doesn't deliver the reliable service it should. And in this context, it's worth mentioning DFS. So DFS is a feature which is mandatory in wireless equipment operating at low frequencies, and basically it provides a priority to radars, so primarily weather radars that operate in low frequencies. And basically it means that telecoms vendors who develop these boxes, to connect points in a wireless fashion, have to back off whenever they sense radar, because radar is considered more important. So that's another thing that's very hard to predict. Next we come to multipath. So multipath can cause significant deterioration in lower frequencies, and it's also tricky to predict because it depends on the terrain. So it depends on how high your antenna is and how high up your antenna is on the far end, and what's around the line of transmission, and all that's going to determine all the echoes that are going to be received at the receiver, not only directly from the transmitting antenna, but also from various reflections, which, as I said, depend on the terrain. So that causes a bunch of problems like attenuation and distortion of the signal. Also causes something called depolarization, where you're trying to transmit in a particular polarization and the signal all of a sudden arrives in a slightly depolarized way. So this is a whole minefield, and then there are other issues like beam spreading, which can happen due to various layers of temperature in the atmosphere. And then if you're trying to do non-line of sight things, then you start getting into diffraction issues around obstruction and that kind of thing. So all of these things, if you wanted your link to be reliable and you wanted to know how reliable it is, then these are all things that you need to quantify, and they're notoriously difficult to quantify. So the good news is that in millimeter waves, none of these need to worry you because they don't exist. Multipath doesn't exist because there are no reflections, because the beams are narrow. There's no interference for the same reason, and all these other bad things don't happen. So really, it's only the rain that we need to be concerned about. And the good news about rain is that it's very well understood. We've got long-term statistics about rain in various countries. In fact, I listed one of the ITU, the International Telecommunication, well-known open database is called ERA40, which basically collects rain information on a 100-kilometer grid across the globe, and it's really available. And you can have a look at that, and you get a very good idea of what rain intensity to predict, and then you can take that into the calculation. And once you do this, you get a very good prediction of your link's performance. For example, if you need a 10 gigabit per second link which operates over 3 kilometers in Oakland, you use this database, you do all the calculation, and you can be sure that the prediction you get for the link availability will be quite accurate. Okay, one thing I do want to mention about maybe overcoming the inherent limitation of short distances and millimeter waves is that some people like to deploy millimeter waves because they're upgrading their connections. For example, they may have had a 5 gigahertz connection which was able to deliver, I don't know, maybe 200, 300 megabits per second, but they need more. So they'd like to put in a millimeter wave link, but they know that the millimeter wave link will not be available 100% of the time, and specifically when it rains heavily. So then what they like to do is keep the 5 gigahertz link in place and use that as a backup. So basically it means that traffic then propagates over the millimeter wave link, offering an air capacity of 1 gigabit, 2 gigabits, 5 gigabits, or whatever it is that you need. And in those very short instances where it rains heavily, then traffic gets automatically rerouted into a low-frequency radio, which is immune to rain. For example, 5 gigahertz, an example. And then you can do that sort of thing with your favorite 5 gigahertz radio or one that you have existing. Okay, so the idea is that you may, for example, get a 2 gigabit connection or a 10 gigabit connection, maybe only 99% of the time, which is not very much. But during the 1% of the time when that is not available, then at least you've got something. You know, you've got some sort of service between the two. And there's a picture I put on there of a 15-kilometer link where at the bottom you see the millimeter wave radio, and on top you see a 5 gigahertz radio. Okay, it's just an example. So that is a way to overcome the distance limitation. Okay, gosh, I need to hurry up. Okay, so for those of you who are hearing millimeter waves for the first time today and think that maybe it's something quite niche, then I put this slide on to try and assure you that that's not the case. So this is a picture of San Francisco, and every one of these green dots is an E-band radio. Okay, so the reason this is easy to plot, because E-band is regulated in the USA, which means every E-band link going up needs to go on the FCC's database, the FCC being the regulator in the US. So then it's easy to take the database and just plot it on a map. So as you can see, it's heavily used. And not only in San Francisco, of course. Okay, there's also a bunch of other applications. So I know most of you are ISPs or sort of related to that industry, but there are different applications, different industries which also make use of this technology, such as smart cities, security, and so on, taking advantage of this technology. Right, so, there we go. So, as I thought most of you would be ISPs or so related, I wanted to show an example of an ISP in the Bay Area in California called WebPass. And they are primarily a wireless ISP using millimeter wave technology to connect the various customers. And you can see, it might be hard to read because the quality is not very good, but you see WebPass is the fastest ISP because they're using this kind of technology that does allow them to have really fast connections. In fact, they were so successful that Google Fiber, who was set up to bring fiber to every home, actual fiber to every home, decided to purchase them because bringing fiber to every home proved too daunting, even for Google. Okay, so this kind of shows a typical use case of millimeter waves where you may have fiber reaching some buildings in a neighborhood or a business park or what have you, and then the idea is that you want to extend the fiber footprint to other buildings, in which case you can use something like E-band, for example, where E-band delivers the higher capacity, like I said, to 10 gigabits per second, even more. And then maybe for the access bit, use the unlicensed 60 gigahertz. It's just a typical use case. Okay, so I'm now moving to the second part of my presentation, which is to talk about how to use this technology to bring gigabit to the home. So I talked a little bit about fiber extension, that's particularly E-band, but I want to talk about something more interesting now, which is how to use V-band for the access. Okay, so with V-band, with 60 gigahertz, there is a really important, I would say, technological process going on at the moment, or has gone on, which is Wi-Fi taking or embracing 60 gigahertz as their next Wi-Fi protocol. So as you can see here, 802.11ad, also known as WiGig, that's been ratified, and then they're working on the next one, which is called 802.11ay, okay, which will bring various enhancements compared to AD. And I also put another one on here called Teragraph. This is a Facebook initiative to do things a little bit better. But irrespective of what it is, it means that the big players, such as Intel and Qualcomm, are interested and are producing a chipset for these frequencies, for these applications. And that's always good. It's good for the consumer, good for the customer, because it means cost is going down, and it also means that footprint is going down. So I brought an example to show you. So this little box here, for example, operates in 60 gigahertz and will provide a gigabit connection. So you can put that on your terrace or behind a window on your home, and that's it. And you've got a gigabit connection. Okay, so that is really the power of these chipsets. Also, what these chipsets do is they support something called beamforming, which is very important. So I mentioned before that the beams are narrow, which means when you normally put these links up, you need to take care in aligning the antennas in the right direction. With beamforming, that's all done electronically, so you don't have to do that. So something like this will cover a sector of, say, 90 degrees, or some maybe slightly more. And so it means that putting these up, you can actually email these, post these, not email, not yet, but post these to your customers and say, just put it on the window that faces east, because this is where we have our access point, and it will automatically connect in the right direction. And just to say, because we're talking about sectors, those of you who have used 5 gigahertz before, they also cover sectors. But these sectors, that means that the transmission is actually 90 degrees wide, whereas here I put this, it's a little bit technical, but it shows you that in these frequencies, in millimeter waves, the beams are still narrow. So although they can scan in a wide sector, they're still very narrow, keeping the interference down and all these other good attributes which I was talking about before. Okay, so I see I'm running a little late, so I'm going to hurry up a little bit. So just to say, when trying to, or when planning networks to bring gigabit to the home, there are various, I would say, topologies or architectures that people look at. Some people like to have redundancy, so they're looking at rings, so Ethernet rings, which have inherent redundancy. Okay, as you can see here. So this is just one example from the US, and this is perhaps a more interesting one. This is using a point-to-multipoint system, with a scanning beam, as I described before, to connect homes. This is in Georgia, in the US, and you can see the different colors of the lines connecting. These are the actual beams, and being the same color, meaning they're sort of within the same sector. And in this example, there's 350 homes, all connected, all have gigabit connectivity. Okay, so the last thing to say is that when trying to bring gigabit to the home, it's not enough to have the right hardware. Obviously you need to have a low-cost device which is able to deliver that kind of capacity. But we find more and more that people need access to planning tools, because the challenges here can be quite daunting. So this is an example of a neighborhood in Mississippi, again in the USA, and each one of these red dots is a home, and each one of these red dots wants a gigabit connection. So how do you plan the topology for this? Are you going to go for point-to-multipoint? Are you going to go for rings? Do you want redundancy, yes or no? So to a great degree, that depends on the business logic of the organization. Some ISPs like to put the infrastructure up there, believing that the customers will then come along. Others would like to sign up customers first and then put the infrastructure in. How do you pick the asset location? So, like I said, this is all a line of sight technology. So ideally, you'd need a point that's quite high up in order to see all these houses. So how do you pick it? How do you optimize on your asset location? And then, of course, it would be nice to be able to automate line of sight calculation, because the obvious way to do this is to send somebody to site to make sure there's a line of sight. But when you have that many homes, it's just not viable. So the data is available today. Lots of places have LiDAR data, which is available. Google Earth does quite a good job of providing that. So it'd be nice to be able to look at a neighborhood like this and be able to tell straight away where are the possible lines of sight. And then we go on from there to a link availability calculation and even equipment configuration. Okay, so you don't want to have to configure individually radios in each of these homes. Okay, so I hope that gave you a taste of millimeter waves and how that can help with fixed wireless access. Any questions? Oh, this one there.
Yeah, okay, very good. I assume somewhere there's going to be a question about how hard fibre to the home is.
You was talking about mounting them to windows.
Sorry, I can't hear.
Sorry, a little further away. You were talking about mounting the access point or the client radios to the windows. How's the attenuation through the glass?
So usually not very much. It depends, of course, on the type of glass and how much metal there is in the glass, but usually I would say 2-3 dB. And that's assuming that the angle of incident, which means the angle that the beam is hitting the glass, is, not extreme, not very much.
Anyone else? All right, very good.
Okay, thank you
very much.
Thank you.
Alrighty, so next up we have Kay Kachow talking about how to get your network ready for 5G.
Hello in August, good afternoon, and thanks Nathan for the introduction. My name is Kay Kit. I work for Cisco Systems as a solution architect. And you'll be glad I'm not going to talk to you for another half an hour about 5G radio. What I want you to do is probably just do like a soft reset, right? Because a lot of the customers I speak to, 5G is a very hot topic, right? Everybody is talking about 5G, SDN, automation. 5G is very hot. But how do we get our networks ready for 5G? And I want you to think about 5G is not just a radio technology, but I want you to think about 5G as the next frontier to communications, right? The next thing that's going to happen in the world of communications. And all of us are in the world of communications. So just to give you an analogy, we are in a land of great surfs. So I just want to give you some inspiration with a picture of a nice surf. I'm not sure if this is actually New Zealand, but it looks very nice. And my analogy is that 5G is like this big wave that's going to come, right? Some of you in this room will be smashed by this wave. Some of you in this room will be riding this wave. Hopefully none of us will sink and drown, right? So my question to each of us in the room is, are we ready for the fifth frontier? But a more intriguing question is, how do we get ourselves ready? What do we have to do? Do we have to do nothing, right? So just to give you a bit of perspective, 5G is going to be very, very different from the previous 3G and 4G as we know it. Right, we have our mobile devices, 3G, 4G. What is the real difference, right? So if you look at 3G, I'm not going to talk about 1G, 2G, right? Hopefully, we don't care anymore. 1G and 2G are purely about how do we make a voice call without having to have a wired telephone connected to it. But the fun fact that I want to give you is that for this whole week, I just checked on my phone. I made exactly one phone call this whole week, right? And that was yesterday evening. I was trying to look for my colleague because he says he's in a bar across the road. I'm just kind of curious which bar, right? And of course, he didn't answer his phone. So he WhatsApped me back, right? So there you go. So phones are no longer about phone calls. In 3G, I think the emphasis is about delivering a really useful mobile data connection. And when we go into 4G, again, how this changed our life is that we start to use less of the mobile data, but we use more of the mobile applications, right? Things like WhatsApp, we've done a bunch of Slacking, YouTubing and Facebooking, checking our emails was kind of like past, right? We don't do that anymore on our phones. But when we go into 5G, I want you to think about 5G as a capability that will bring us new kinds of ways to use the mobility that we're going to have, that 5G is going to bring, that is beyond just consumer mobile. When I say consumer mobile, means your handset with a SIM card. And in fact, if you look around, there's a lot of press release about 5G. A lot of service providers, the first use case for 5G is around mobile broadband, right? Pumping gigabits or hundreds of megabits to your phone. But they're really struggling, how do we actually monetize that, right? How much more are we willing to pay for phone line, right? So that's very challenging. And they're actually looking at other ways to monetize 5G. And generally, it's agreed that 5G monetization will come from new services. So I have an example of AR, VR here. This is a very hot area, especially in Japan and Korea. They're very keen on how do we impact on our worldly experiences using the 5G technology. And you can see here at the bottom, this is some of the use cases that's being trialed worldwide right now. So you can see things like remote car software upgrade. If you think about our cars, more and more software content are being dumped onto our cars, right? My 1990 Toyota, not much software. If you're going to buy a Prius today or a Tesla today, there's a whole bunch of software, a lot of operating system running in your car. It's kind of like your routers, right? You need to upgrade them from time to time. And how do you upgrade cars that are running on the road without bringing them back to depot? You need to have a pretty good mobile technology that goes to the car. So that's just one use case. Other use case, for example, like a network as a service. For the police department, they need to have a special slice. We talked about network slicing yesterday. Hospitals, remote surgery, things like that. Smart city is another hot topic. And of course, we talk about augmented and virtual reality. 3GPP is a standard body that is standardizing or trying to create standards for 5G communications. They reckon that 5G will bring three broad categories of capability. The first one, which is quite widely talked about, is the massive bandwidth, much more bandwidth than what you get in the previous generation. But on top of that, we also need to think about new use cases that will leverage on low latency communications, right? 5G will bring much lower latency, and then that will allow us to do a lot of real-time stuff that we normally cannot do on the previous 3G and 4G. And also massively scalable communication. So how do you connect everything that surrounds us, our watch, our car, our light bulbs, right? We talk about that. So the key is not just to deliver each of these capability. Oops, why is it going back? Okay. Apparently I have to click at the edge. So if you think about all these applications running on your network at the same time, it's kind of like our MPLS VPN. We have various VPNs running on the same network at the same time. They have conflicting requirements. They have needs for different quality of service, for privacy and things like that. But more importantly is how do we deliver all these things reliably across a single network, across a single IGP, right? You don't want to run different IGP for different applications. So I just want to use this quote from Olivier Pozet from Sierra Wireless. So he said it pretty well. He said, fast is good, but what good is it to get more data if you're sloppy about what you're doing? So 5G is not just about having a lot of data. Say, for example, if I just take a case of remote surgery, right? Someone is going to get cut by a knife. It's got lots of data and very low latency, but not very predictable. Then it's not very useful. Okay, so how do you deliver all these angles at the same time is very key. And all of us are network guys here. We understand that this is way beyond just having a 5G radio. There's a whole bunch of stuff that you need to do in terms of getting your network ready. If you want to be part of this value system of delivering all these new 5G use cases that will touch on all our lives, your children's and your grandchildren's life. And that's what I'm going to talk about. And you look at what goes behind the radio are the networks that we build, right? So you'll probably be familiar with some of these like IP core, central DCs, HDC, and we have new terms coming out like backhaul and front haul, and new requirements that go into that to enable our networks to carry all these new 5G use cases. And on top of that, a lot of our applications today are very centralized, right? A lot of us build networks where we have 3 or 4 central DCs around the country. This is going to grow, right? There will be a lot more new distributed micro DCs that will be instantiated like mushroom around the network. So how do you handle that? Do you have that in your network to support these kind of use cases, right? If you don't, then probably the person sitting next to you is going to get the business, and hopefully he's your colleague, right? Not your competition. So use cases like IoT applications, analytics, they require to be placed at different parts of the network. Say, for example, if I were running edge analytics, I don't want to be able to bring all this streaming big data traffic all the way back miles to Auckland, right? I have to be able to do some pre-processing very, very close to where the edge is. Whereas others like IP offload, CDNs, probably a bit regionalized. And you think about it, all this virtualization and all this additional complexity makes it impossible for us to run the networks the way we run them today, which is hopefully not too manual, right? Hopefully not too much CLI. Hopefully you guys are starting to go into programming and try to understand how we can use tools. There was a lot of talks about tools over the past 2 days and more in the workshops. Oops, now it auto-forward. How do I go back? Okay, so we come into embracing automation and telemetry, and I truly believe that it will be very key for all of us network engineers to learn how automation and network telemetry will impact on the way we run our networks. So I want to focus my talk on the 2 parts today. One is around the re-architecture of the network and what kind of transformation you need to do. Not in this 1 year, but in the next 5 years, so you've got time, don't worry. And also how you run the networks, how you change the way you run the networks. In 5 years' time, you will be very different from the way you run your networks today, hopefully. And of course, then, how do we actually extend this to the public cloud, right? We've got some participants here from cloud providers as well. You need to think about, as a cloud provider, will you be able to play a role in these future 5G use cases? Right? So we are more than just conduit players providing bandwidth or connectivity in this world of 5G. Oops. Okay, so what does this new 5G radio network look like? I just want to give you a glimpse. Nobody has the answer today. But generally, the agreement is that, number one, you need to have any-to-any connectivity, because in the new world, the content, the applications are going to be distributed in different parts of your network. Our networks will stop being just a static pipe. You need to be dynamic to cater for all these kind of applications that need to be instantiated in different parts of the network. And our networks need to become service aware, right? A lot of us are doing traffic engineering today, basically just to distribute the traffic or to load balance the traffic, make sure that our links are equally utilized. In future, you need to do different kinds of traffic engineering at the same time to make sure that you're meeting the SLA of, say, autonomous vehicles, right? Of, say, the police department or remote surgery. And you need to have a new class of reliability, right? 0.1% packet drop, probably not that good enough if you are doing remote surgery, for example. And I want to talk about clocking, because I don't mean NTP, right, here. What I mean is using the network for synchronization purposes, because with 5G, there's a whole bunch of new things like MIMO, collaborative MIMO, massive multi-in or multi-out, that require different kind of clocking from the network that we're going to build as a transport. And of course, others like, for example, we need to be able to reduce the touch points so that we can easily instantiate this network slicing. And also end-to-end security. We had a lot of talk about security today. You can think about it, if your house, your home, your car, everything that is related to your safety, your privacy, is connected to this 5G world, the attack surface is going to be very big, and end-to-end security will be very, very important. So just to bring us back to this mobile evolution, what changes from 4G to 5G that makes it so critical for us to think about 5G from a network perspective. So two things. One is the disaggregation, and secondly is virtualization. So you can see here, okay, I actually have a pointer. From the 4G perspective, the mobile packet call and the radio are pretty static and pretty discrete. But as we go into 5G, they become to be disaggregated, meaning they get to be broken into small different pieces. And if you look at the EPC, which is a packet call, oops. It needs to be broken into the control plane and the user plane, right? So the user plane gets separated from the control plane so that it can be distributed and you can do edge offload and CDNs. And at the same time, coming from the radio, on the radio side, again, disaggregation is happening. So no longer are you going to have monolithic radios. Those radios will be broken down into radio unit, centralized unit, and distributed units, right? All these units are going to be distributed in your networks, and they're going to demand different kinds of transport services from you. So what this means to us, network builders, is that the way we build our networks need to change from very structured, very hierarchical, very north to south approach to more east-west, any-to-any distributed approaches. And at the same time, you'll find that a lot of the traffic will be staying in the metro. I'm pretty sure you are like monitoring your traffic, and you are going to see the trends. Less traffic are going across the backbones, more traffic are going to be localized. And because of all these concepts, all the service providers I speak to, they are interested to move from their current unified MPLS solutions towards segment routing. And we had a few topics on segment routing yesterday. So hopefully that was useful for you. That is going to be key, right? For us to deliver this new 5G world, there will be embodying simplicity, automation, virtualization, massively scalable networks that will be very, very flexible and very dynamic compared to what we have today. So I just want to take on one example. So coming back to the three pillars, right? So you're going to imagine you're going to have different applications that require different components of bandwidth, scale, and latency. If I were to bring all this back onto a single network, I need to be able to do network slicing. And what does that look like? I just want to give you an example here. Okay, there's a delay. So just to give you an example, on the same network, I'm going to be running different services. And these services are not just having isolation between them or different quality of service, right, which is what we are very used to in the MPLS VPN world. But they will also need to be optimized for different things. So if you think about it, the first one is data traffic. EMBB is massive broadband. And in a massive broadband, you need to have coverage, you need to have multiple IP VPNs per slice, a lot of different QoS classes and things like that. Then you have a low latency slice. Maybe it's a microsurgery or it's autonomous vehicles, right? You need to have very, very predictable latency. And you have other slices, like, for example, machine-to-machine, which needs to have scale and other things. So all these slices, you can think of it as running a network with multiple topologies or multiple virtual topologies on a single IGP. So what does it look like? So you can imagine I'm going to create all these different slices, and they're going to be end-to-end in the network. So some people think that, look, 5G network slicing is just about, look, I'm just divide up my spectrum on my radio into multiple, or I'm going to have my DWDM divided into multiple. That's not the case, right? Because it needs to be end-to-end. Because if you think about it, the services are coming from the data centers all the way to the users, and the users can be anywhere in your network. So that's number one. Network slicing is end-to-end. And secondly is, how do you bring up, how do you spin up all this slicing as and when your customers require them, make changes to them, and remove them, right? Some of these slices can be long-lived, some of them can be very, very short-lived. So that means we need to have an end-to-end orchestration. We can't use CLI to configure every routers to kind of create this kind of environment manually anymore. And secondly is that there's two types of network slicing, right, in general. The easy one to understand is hard slicing. Hard slicing, for all of us who are in the network environment, think TDM. Right? Hard slicing is where you dedicate resources in your network. Say, for example, particular waves in your DWDM network, or particular time slots, or particular routers in your network. They are dedicated to a slice. And whatever is dedicated to one slice cannot be shared or used or multiplexed with other slices. So that's hard slicing. But the more interesting one is actually soft slicing, because all of us, we are running networks where we statistically multiplex, right, different applications. And that's what we need, right, in this new 5G world. And this is where soft slicing comes into the picture. And yesterday, Richard gave you a demo about flex algo. So that's one way to do soft slicing, where you provision resources according to the slice, but resources that are not used by one slice can be used to service other slices. Therefore, the efficiency is going to be much higher than a hard slice network. So in a real network, you could use one or both, but I truly believe that soft slicing will definitely play a big role in your network. And then you need to think about how do you actually do this soft slicing in your network? Are you ready? What are some of the components that you need? So at the base of it, the first thing you need to do is that you need to do some housekeeping, right? We talked about state. I think it was Jeff. He said very well about state. So over the years, we have added a lot of state into our network. And when we have a lot of state, our network cannot scale, right? We need to start to remove all this scale from the network. And this is one of the key reasons, if not for others, that service providers are starting to employ segment routing in their network to remove state from the network and to bring simplicity back into the picture so that they can scale. That's the only way. And also, segment routing gives you a very simple way to deliver resiliency in your network, failover, without the complexity of RCPTE, tunnels, detours, and things like that. And as well, the other piece that I think was slightly touched by some of the other presenters was streaming telemetry, and I'll touch on that a little bit as well. Because now our network needs to be service aware, right? We need to know what's happening. We need to know how the services are experiencing in our network. What are their experience? What are their, what are they seeing, rather than what we are just seeing as a network operator. On top of that, we need to stop thinking about our network as a collection of devices connected by wires. We need to think about our networks as a system. This is where PCE controllers are coming into the picture, because that will bring us a multi-domain view. A lot of us run networks that are multiple IGP, very distributed, but how do you actually have an end-to-end picture of the traffic engineering topology, utilization across the whole network? And the second part is that it brings you a northbound API. Then now your network becomes programmable, and you can run software or integrate software capabilities on top of your network and deliver the end-to-end SLAs. The third piece that comes into this is Flex Algo. This is a very new standard in the IETF. And this is where I start to bring in the capability to run multiple customized IGP algorithms on the same single IGP network. So I'm still running the same network, but I can create different sub-topologies, if I like. One topology for connected cars, different topology for the police department, and another topology for the general purpose, for example. Right? And each of these topologies could be optimized for different things. One for latency, one for IGP metric, one for reliability, for example. Then I just want to bring you one slide on clocking. A lot of us probably don't think very much about clocking. I personally didn't think very much about clocking because the most important thing for us is reliability, right? Our networks are up, they're running. We don't really care very much about clocking, but when we come to 5G, clocking is one of the key requirements as you build your network. And I just want to give you some examples here. These are actually the standard that the industry is driving. So if you look at the general 3GPP LTE, that's what we have today. If on our phone you have LTE, that requires 3 microseconds of error in the clocking, right, in the movement of the clocking. But as you go into more advanced use cases like MIMO, the tolerance to this error becomes much less, from 3 microseconds to nanoseconds, right? So when you build your network, you need to think about new clocking standards that allow very, very accurate clocking to happen across your network. And also, you can see the accuracy budget. We used to be in the existing Class A and Class B. Now we are proposing the Class C. Again, you can see the budget has decreased by 5 times, 2 times, compared to what used to be before. And because of this, we need to have hop-by-hop clocking. That means if your equipment today are not running clocking, in future, it has to run clocking technology, right? Your network needs to support clocking standards. So if you're going to build a new network, make sure that you can support clocking. Otherwise, it's not 5G ready. Now, shifting gear from building networks to operating networks. So when you go into the 5G world and in general digitization, the number of things that we need to manage, be it physical or virtual, grows by 10-folds and 10-folds and 100-folds. And if you look back from the ages of the mainframe, right, we have very few devices, we have very few monitoring tools, we have very few changes in the network. We have a lot of humans catering for these very few devices. But today, we still have pretty much the same number of headcount, right? It's pretty difficult to get headcounts. Whoever is having a very easy time getting headcounts, please let me know. But at the same time, we are tasked with addressing more and more devices and virtual devices that sprawl in our network. So therefore, we need to have new ways of managing the network beyond current manual processes. So a lot of us have networks that are run by rules. So we design rules that map out how the network should behave when certain thing happens. But from this very static view to the world of SDN, NFV, virtualization, IoT, we will start to see that dynamic algorithms will start to replace these rules, right? We talk about Go and we talk about Python. The reason why all these topics are becoming very interesting in the world of networking is because we need to be able to build new algorithms that understand what is happening in our network, do some machine learning, and then reactively update our network or self-heal our network. So in general, we call that AI ops, right? It's a new way of using AI to run our operations. So that is enabled by streaming telemetry. Obviously, you can't manage what you can't see. And streaming telemetry will be very key because it brings you a more scalable way to collect data from the network using a push approach. That means from the network, I'll just push, just like a magazine subscription, I'll just tell the magazine provider, look, I want to have this magazine 5 times a year or once every month, and then I don't have to say anything. Network will just push it to me. And I can push it in a format that is analytics ready. So I can push it in JSON, in XML, in formats that are very, very easy for machines to understand. And what is more important than telemetry is model-driven telemetry because there's a whole bunch of data in the network. How do you define and how do you explicitly and precisely say what kind of data do you want to collect? And I just have some example here where you see we will need to model a generic network device into interfaces, speed, duplex, and things like that. And we create Yang models of what are some of the things that we are interested to collect. And this is what we will call model-driven telemetry. It gives a very consistent and very complete way to describe what we want. And when we put all these things together, this is what possibly your new generation network will look like in 5 years' time, right? If you are kind of progressing towards that direction. So we talk a lot about the network infrastructure, and you'll see that we will have model-driven software capability into every layer of the network. So starting from the network infrastructure itself to telemetry and analytics, path computation, service orchestration, all of this will be defined by data models, and all of them will expose API that allow them to be connected together and for you to integrate external systems into your network. So no longer are our networks like a closed system. It needs to become an open system, right, that is connected to different things. So in summary, I talked about 5G and how 5G will expand telecommunications beyond consumer mobility into something that will touch and change the way we use technology in our everyday life, right? Our cars, our houses, our light bulbs, and things like that. And this will herald a very deep network architecture evolution in the networks that we build. End-to-end thinking will become very critical. And lastly, new programmability networks approaches and NetOps and AIOps approaches to handle the scale and dynamism will be key for us to think about as we move forward. So lastly, thank you and enjoy NZNOG. Thank you very much for your time.
No, it doesn't look like it. Okie doke.
Thank you, Nathan.
All right, thank you very much. Alrighty, so we've got a break now. It's, I think, about 30 minutes. Yep. We'll start at 3:30. Yeah, okay, yep. So yeah, we'll start at 3:30. So I guess coffee and so on out in the hall. Great, thank you very much. See you back here in 25 minutes.